In this video, we'll discuss self-attention, a crucial component of transformers that allows elements of a sequence to attend to other elements of the same sequence. Let's dive right in. Self-attention. Before we go into the inner workings of self-attention, let me give you an intuition and interpretation of attention that I find very useful, namely that as a soft retrieval from a database. So if we do retrieval from a database that has key value pairs, just like a hash set, for example, what you do is, well, you have a query queue and you compare this query queue to each of the individual keys. And if you have an exact match, let's say here for key 3, then you return the value at that position. So that's what happens in database retrieval. You compare the query to the keys and return the value of the exact match. Written in terms of a formula like this, you have an indicator function for the query matching a particular key, and you multiply this with then the value at that position I. And you sum that over all the positions because you only have one exact match in a database and in a hash set. All right, so that's database retrieval. And a soft version of that would be saying, well, you don't have to have an exact match, but you have a score how well your query matches each of the keys. And this is a score between 0 and 1, and you multiply your values by this particular score. This would then give you a soft retrieval from this database where each of the values gets to weigh in, and it gets to weigh in by, well, how strongly its keys are aligned with the query. So you have a similarity function where you compute the similarity between your query and your key, and you do a softmax of that, and that's the attention weight with which the value is being multiplied. Now, relating this to the type of encoder-decoder attention we've seen when we looked at attention for improving RNNs, we also had a similarity function like this. And in particular, we computed the similarity of the query being the hidden state of the decoder, and we compared that to the individual hidden states of the encoder. And then we again computed a softmax, and we multiplied this then with the actual encoder state. So the encoder hidden state that was called H at that point, and that would go into both the value and into the key here, and the hidden state of the decoder that we had denoted as S sub t minus 1 at this position t minus 1. So this interpretation of attention as soft retrieval from a database actually directly explains what was happening in our encoder-decoder attention in the context of RNNs. And we're also going to use the same mechanism for self-attention, except that for self-attention, we're actually going to use the same set of embeddings to generate all of the keys, values, and the query. All right, so I've written this formula here, and just for completeness sake, I have also written out what the softmax is. It's nothing else than e to the power of the similarity, and then you normalize by the sum of each of the individual locations, each of the individual keys. All right, so this is a very general way of computing the attention score for a set of queries and keys and values. And one component that is not fully specified here is, well, what is actually the similarity score between a query and a key? And well, for this, actually, we can use different types of similarity functions. We could, for example, just use a dot product, and this dot product basically is large. We can visualize this, the dot product between two vectors. Let's say this vector and this vector is very high if they're pointing in a similar direction, and it is very low for two vectors that are pointing in almost orthogonal directions. So this dot product can actually be a very nice measure of the similarity of two vectors. And actually, many of the different types of similarity functions here are just variants of this dot product. So here we have a scaled dot product, and here that is basically just a dot product, and we divide this by the square root of the dimensionality of this vector. And this is actually the type of similarity function that is used with transformers nowadays. And the reason that this is used, the reason it's better than a standard dot product, is that it gives you some amount of invariance to this embedding size that you choose. Transformers tend to do better if you use a larger embedding, and if you have more compute, then you typically use as large of an embedding as you can get away with. And if you didn't normalize here with respect to the size of this embedding, then, well, the value of this dot product of these two vectors would just grow the larger your embedding size gets, and then you would have to actually retune your parameters if you were to change your embedding size, and that is something that you, of course, would rather not want to do. Then here we have another generalization of the dot product, where you have a weight matrix W that actually consists of trainable weights. And so this is strictly more general than the dot product, and actually also more general than the scaled dot product. It could learn to do the same as a scaled dot product, but of course, well, it includes trainable parameters, so you pay for this generality, and it might actually not generalize as well as a simpler form that doesn't have this trainable weight matrix. And finally, this form here is a additive similarity, and this is a type of similarity that also now includes trainable weight vectors here. And well, this is actually exactly the similarity that you would compute with a linear layer, that you feed in both the q and the k sub I. They go into this little layer and are multiplied with weights and then summed up. And this here is just a small selection of possible similarity functions. You could also think of other types of similarity functions. And indeed, there are some others in the literature, such as a cosine similarity and so on. And you can also think of, well, just making a relatively complex neural network in order to compute the similarity of two vectors. And well, we'll see whether future years will change the similarity metrics that are used in different variants of transformers. But for now, what is used in transformers is the scaled dot product. All right, so let's get back to self-attention. Why is this called self-attention? Well, it is called self-attention because we'll actually attend to the other words in the same sentence. So we construct the queries and keys and values all from the same sequence of inputs. Recall, for the encoder-decoder attention, we used the hidden state of the encoder both for the keys and for the values, and we use the decoder hidden state as a query. And in self-attention, we'll actually compute all of the queries, keys, and values from the same sequence of inputs. So whereas in encoder-decoder attention, we use this attention mechanism in order to relate one sequence of words to another sequence of words, here we relate a sequence of words to itself. All right, let's visualize this. So here is a possible sentence that we might want to apply self-attention to, and it reads, "The animal didn't cross the street because it was too tired." Now, this word "it" could potentially relate to the word animal, or it could also relate to the street. Now, the street is actually much closer to it, so for example, an LSTM type mechanism might actually think that it probably relates to the street because street is relatively close. But in this case here, clearly it relates to the animal. And the self-attention mechanism here can actually compute a weight that relates the embedding of the word "it" in this layer here to the embeddings of the various words in the previous layer. And we see here that the embedding for this particular word "animal" is actually quite large. It's actually also large for the word "the." And in this particular case, for street, it's actually not quite as high. And well, this is actually, in a sense, the right interpretation. We don't want it to mean the street, but we would like it to basically be read as a synonym of the animal. So the sentence would be correct with the same meaning if it read, "The animal didn't cross the street because the animal was too tired." And because of that, it actually makes a lot of sense that the animal actually has quite high attention weights in this case here. So this also tells us already a little bit about what self-attention does. It allows us to change the representation of the word "it" to take into account the context in which it is presented. Now let's look a little bit into detail to see where these keys, values, and queries actually come from in our input sentence. So for each input x sub I, so each word or each embedding of each word x sub I in the input, we compute the query, the key, and the value vectors by linear mappings. So that means there's 3 trainable weight matrices, namely WQ, WK, and WV for the queries, keys, and values respectively. And for example, multiplying x sub I by WQ produces Q sub I, the query vector that is associated with the word xi. We can visualize this as done here. We have a sentence that contains, again, 2 words, thinking machines. Each of the words here has an embedding, x1 and x2. And if we multiply x1 by WQ, then we get the values in the query Q1. And likewise, if we multiply x2 by WQ, we get the query Q2. And likewise for the keys and the values. So now that we have computed these queries, keys, and values for each of our inputs, we can actually compute our self-attention weights. And so, as I mentioned before, in transformers as a similarity function, we use this scaled dot product attention. So we have a dot product scaled by the square root of the embedding size. For example, now if we want to compute the self-attention for the query input x1, we compare the query for this x1 to the key for x1, and we compare the query 1 to the key 2, and this is happening down here. So we have the queries, keys, and values for our input 1, and we have the same for our input 2. And so here we compute this dot product for query 1 times key 1. Here we do query 1 times key 2. Then we divide this by the square root of the dimensionality of our embedding, in this case here, this is 8. And we compute a softmax in order to have values that are between 0 and 1. And so we find that the similarity between the query for thinking is higher with the key for thinking than with the key for machines. So we're going to use more of this value vector than of this value vector. So that's precisely what's happening here. Here we now also take this softmax here and we multiply that with this value, and then we add this softmax times this value. And this is our resulting sum that is now the transformed representation of our input. And so that's how self-attention works. You basically compute the similarities of the embedding of a word multiplied with the query matrix, the WQ, the trainable weights, to get the query from the embedding. And you compare that to the keys of each of the individual inputs, and then you use more of the values for the individual inputs for which the keys are closest to your query. And so you transform the representation of each of your individual inputs to become, or to incorporate a little bit of all the other embeddings of the context in which your word occurs. Now, how do we actually compute this in matrix form? So we have a sentence that has 2 words. That's why the dimensionality of this X matrix here is 2 by, in this case here, 4 in this small visualization. In practice, it's often 512. In the original paper, it's 512. And you multiply this with the trainable weight matrix for the queries to get this Q matrix. And so this dimensionality here is also 2 because you still have 2 positions. This dimensionality here is often smaller, and we'll see in a second why it is. And the reason is that we have multi-head self-attention, in which case this here is going to be 8 times smaller than this dimensionality here. So in the original paper, this is 512, and this here is 64. And we'll see with multi-head self-attention why that is. But so we do the same thing for the keys and for the values, and get out these query, key, and value matrices. And then we can compute the softmax very nicely in just one line. So we multiply this query matrix here times a key matrix transposed. We do the rescaling, and then we take the result of the softmax and multiply it with our value matrix. in order to get our final self-attention matrix. And again, this final self-attention matrix has a dimensionality of 2 because there is 2 positions, and it has a dimensionality that is the same as this value matrix here. And in this case here, this is also going to be 64 because we have multi-head self-attention, which is what we're getting to now. So multi-head self-attention aims to attend to more than one concept at a time. And the reason why this is a good idea can be illustrated by looking at a sentence very similar to the one we saw before. So this one here is, the chicken didn't cross the road because it was too wet. Before we had because it was too tired, and there was clear that it was referring to the chicken because the road can't be tired. But now that we have wet, well, we could have a chicken that is very wet and doesn't really want to cross a road, or we could have a chicken that doesn't like to cross the road when the road is wet. And these two sentences have very different meanings for the word it. In one case, it should be a chicken that is wet, and in one case, it's a road that is wet. And both of those could have some high-dimensional embeddings. And if we didn't have multi-head self-attention, then we would be forced to actually average over these concepts, and that would mean averaging the high-dimensional representations for these different concepts, namely a chicken that is wet and a road that is wet. And it is very unclear that we actually just want to average these. Rather, we probably want to have one interpretation of the sentence where we're talking about a wet chicken and one where we're talking about a wet road. And then at the very end, we might want to average predictions of these different concepts, but not too early when we're talking about the individual representations of the word it. So how do we get this multi-head self-attention? Well, we simply have actually more than one attention head. So we had one of these z's before that we would calculate with the equations that we saw on this slide here. And now we just have these equations here multiple times. In fact, we have them 8 times in order to get 8 different attention heads. And so this is where it comes in that the original embedding size here is actually different than the size of these embeddings here. In the original paper, this here was 512, this here was 64, and that was the case because we had 8 of these different attention heads. And so then in order to put this all together, how can you compute all of these different attention heads and what do you do with them then? Well, you simply do the same type of computation that we did before. So on the previous slide, we had this computation already for one of these attention heads, and you simply have the same computation 8 times. And then you concatenate these attention heads here, and you multiply them with this matrix here, which is this output weight matrix, in order to get a embedding that is now actually of the same size as the input embedding. And in order for this to happen, you don't necessarily have to have the fact that when you have 8 heads, that the embedding size of the individual heads is 1/8 of the original embedding size, but it is convenient in terms of using all your memory, and so that's why this choice has been taken. So this is a full picture of multi-head self-attention, how you can actually compute this in matrix form. And yeah, we have the whole picture here of having, well, 2 words having the large embedding for them, then for each of the individual attention heads having a smaller embedding size, still for 2 words, concatenating all of them, multiplying them with this output weight matrix to get again for these two words the original large embedding size. And this brings us to the end of this lecture. And as always, I'd like to leave you with some questions for you to activate the material. I'll see you in the next video. Thank you.